Good evening, everyone. My name is Madrina Chirija, and together with Tuhai Seijin, we're going to take you through the topic that was allocated to us, that is graph retrieval augmented generation using knowledge graphs and vector databases. Well, the component, when we move on to the next slide, we're actually going to notice that the components that the contents of the video. The first content is going to be the introduction to retrieval augmented generation. Then furthermore, we are going to look at how best we can understand knowledge graphs and then understand the vector databases. And then after, in the last bits, we shall learn how to combine both of them together and we see how they all work hand in hand. Yes, so we can move on to the slide 3. Kindly move to slide 3, Eugene. Well, on slide 3, we are going to start by introducing the retrieval augmented generation, as I talked about it. Well, we're looking at graph retrieval augmented generation. I hope we all know that. And but we're going to first split this thing and understand what is actually a retrieval augmented generation. Well, a generation is a large language model that provides a response when a prompt is given to it. But these responses sometimes are out of date. Sometimes they have no source where they're getting their information from. Take an example of you make a prompt of how many moons are maybe on which planet has the most number of moons, and then the model provides for you Saturn as the answer. But okay, Saturn does exist, but you are not so sure that it's actually the right answer. So when we implement retrieval in it, retrieval is going to help us fetch information from external databases so that by the time the system is providing you an answer, it's giving you an answer that is up to date and it actually has a source of the information. So retrieval augmented generation is the process of optimizing the output of a large language model so that it references an authenticative knowledge base outside the training data. Because when you're training the model, you're going to train it on the data that you've given it on the data sets. But when you give it a prompt, it's not supposed to base on only that. It's actually supposed to at least figure something out. Okay, it's going to make patterns, but it's not good if it only bases on the local data you've given it, it won't be able to give an answer that is up to date. And that's going to make you have to update it all the time, keep it up, and that's a lot of work. So when you introduce this element, it's going to help it fetch information from different places so that it provides better responses. So moving on to the next slide, we are going to talk about how important the retrieval augmented generation is actually. So we are going, I've talked about it having okay, you don't need to update it all the time. So when there is retrieval augmented generation, that's abbreviated as RAG, it prevents daily updates. You don't need to update the system all the time. And it allows the model when to say that it does not know, because it's going to search all the external databases. If it doesn't find something, it's definitely going to return, I don't know. So by the time it returns, I don't know, it has tried. It's not returning, I don't know, because it has not found it in its local database, but it will return, I don't know, because it has tried to search around, it has not found an answer. Then it also helps to give the richest best answer available. Like it will not produce what you specifically trained it on. It's going to research and provide what is the best answer. Yes. So that brings us to the definition of a graph retrieval augmented generation. Well, a graph retrieval augmented generation is a method that is used to improve the performance of a machine learning model, especially generative AI models, by giving them access to external information so that they can provide relevant answers. And we are looking at this in a way that it retrieves information from two sources, as we're going to see. A graph RAG, a graph retrieval augmented generation, retrieves answers, information from two sources. It retrieves information from a knowledge graph, and it also retrieves information from a vector base. So after retrieving information from these two, it's going to match them up so that it can provide the best response. Well, let's start off by trying to understand what is a knowledge graph. The next slide. Well, on the next slide, we're talking about what a knowledge graph is. A knowledge graph is a way of organizing information like a network of connected facts and ideas. So the simplest way I can explain this to you is it's like a network of facts that are connected by something. Well, it has two components, nodes and edges. The node is the entity and the edge is the relationship that binds the nodes together. So let me take an example of there is an entity, like there is an entity who is a person, let me say an entity called Madrid, and then there is also another entity that is maybe YouTube, another entity that is WhatsApp and all that. So in a knowledge graph, we try to find out what is the connection between some entities. So a knowledge graph represents the relationship between different entities. So what's the relationship between entity Madrid and entity YouTube or entity WhatsApp? So the relationship there could be Madrid has a YouTube account. So that part of has a YouTube account, it's the relationship that binds those two together. So that's the simple understanding of a knowledge graph. A knowledge graph is more of a network of connected facts and ideas. So these facts are connected with a relationship. Yes. So on the next slide, I'm going to try to show you an example of a network, a knowledge graph that is talking about the quality of a photograph. So let's move on to the next slide and try to see that image. Well, looking at this image, let's choose an entity like image clarity on the left-hand upper corner. Image clarity is an entity, it's a node. And there are other nodes that are attached to it, like very poor, poor, average, good, excellent. Those are the nodes that are connected to it. So when you look at this, average, let's look at average, let's use average. Average and image clarity have a bond that is connecting them. So that's their relationship. That means that image clarity can be average. So those are two nodes that are being connected by a relationship. Yes, I hope that is clear. So let's move on to the next slide and try to dive deeper in knowledge graphs. So on this slide, we're going to look at how useful are knowledge graphs to a model. Well, to a model, there are basically four hypotheses I'm going to try to explain to you of a knowledge graph. Well, a knowledge graph in the first place is that it creates connections. How? Well, knowledge graphs will help AI models to understand the connection between different pieces of information. So Madrin is an entity somewhere, WhatsApp is an entity somewhere, and those are different pieces of information. So with a knowledge graph, it's going to help the model understand what are those different, like, how are the different pieces connected all together. And then it's also going to help in recommendations, because when, let me say, you are trying to, okay, in a recommendation system, because what we're looking at can also be applied in recommendation systems. So in this case, knowledge graphs are going to help a model in making recommendations, because if maybe you're saying let me see, maybe if you're saying Madrid, then YouTube, WhatsApp, and something, and you're searching something, that model is going to see the relationship between the two, and it will recommend something like, okay, get that person through this. I hope you get what I'm saying. Yes, then also knowledge graphs help to find better answers, because you're able to find an answer that actually connects to what you're talking about. That is a relationship. And then also it's an organizer. Knowledge graphs help to organize complex data from multiple sources, because the data might be a lot. It has different entities, different characteristics, different ways it relates with each other. But a knowledge graph will help to know that, okay, this is connected to this, but not this, and this is connected to this. So when the data is becoming more and complex, a knowledge graph helps to explain or to organize the information and reduce the complexity. Yes. Let's move on to the next slide. Well, on this slide, I'm going to try to take you through how a knowledge graph actually works, the flow. Well, in this case, the system picks out words from the prompt that are important and then uses a pre-built map of relationships to find connected details. So in this case, I'm going to use an example of someone enters a prompt in the model, in the system, and enters a prompt of, I want a delicious pasta recipe. That's the prompt the person is going to enter. So that's the first step. The first step is user query. You're going to enter the prompt. When you enter the prompt, the model is going to pick out key entities, the terms that it actually considers important, that is going to pick out and be like, okay, this and this and this will help me fulfill and give a response that is actually beneficial. So it will pick up, maybe extract important words, like maybe, let's say, for in our example, let's say it will pick out pasta and delicious. So when it picks out these two, it's now going to check in the whole of its, okay, in the pre-built map of relationships, it's going to check through and see how best these words are connected. And when it finds out, okay, how the keywords are connected, and it's going to retrieve this information, and it's going to use this to try to package a proper answer for you, a response that will actually benefit you. Yes. So that's how a knowledge graph actually works. That's how the flow is. It will, you enter the prompt, and then it will extract the entities, the ones that it feels are important, search in the ones that it already has, and then retrieve information that will help you. Yes. On the next slide. Well, on the next slide, now we've talked about knowledge graphs. We're now going to look at vector databases. Remember, we've said that we're going to try to understand how the other part works, how this part works, and then we merge them together. So we've seen how the other part works. Now we're going to look at vector databases. The word databases itself tells you that this is storing something. Okay, storing and retrieving. And traditionally, text was represented in form of text and columns. Like, you store the values like that, and that's how you're going to retrieve them, and they're not going to be modified, manipulated anyway. If you stored it as boy, it's going to come back as boy with no modification. But currently, vector databases are used to store text, images, documents, and videos. Well, in this case, we do not just store the text the way it is. We convert them. And so in this, they are converted to vector indexes to enable efficient similarity searches and retrievals based on the content's characteristics. So when these things are, okay, when let me say the image is converted, it enables retrieval, because large information, okay, when they convert them to vector indexes, large information can actually be stored. And when you're searching on the web or something, it's going to be easy to retrieve those, okay, to get similar searches. Because when you notice that when you type, let me say you type something like cow in a Google browser, and you type that, when you type that, it's going to bring for you very many different types, like cows with black spots, with brown spots, and so many more. So in this case, it's going to just look for something that is similar to what you're looking for, and then it will reproduce. So vector databases actually is similarity searches. Yes, other than just getting the image and then it has to analyze it again, and then until reproduce, okay, like bring feedback. So in the vector, when they convert them to vector indexes, it is easy to search for similar searches. Yes. So on the next slide, we're going to try to expand more on vector databases. Yes. So what I was trying to explain to you is that when we are actually trying to work with this, what I was trying to tell you is that when we're working with this, we convert all this to vector indexes. So an image like that is converted to a vector index of maybe 1.9, 0.3. Now, vector indexing is very different from tokenization. Remember, we say tokenization, they just get the word and break it down. How are you, and then they just split how are you separately. For this case, vector indexing is all about, they convert it to numerical values. And when they are storing these values, they always store them with references, so that when they are retrieving this, they can also retrieve the actual thing, the actual image. I hope you get what I'm saying. Yes, so this is an example of how the vector indexes actually can occur. They transform the words, the text, the images, even documents. Just that I use 3 examples here to try to show you how the conversion takes place. Yes, on the next slide. On the next slide, we're actually going to try to see how best we can, we're going to see how the vector databases work. And so in this case, they work in a way that the data is converted into vectors, where documents can be converted using Word2Vec or But then visual images can also be converted using CNN, that's convolutional neural networks. Then there is a bit of indexing in it. So advanced indexing mechanisms are used so that when they are storing that convert the vector index, it is also attached, like they store a reference to it so that you can at least retrieve the image when maybe you're searching for an image or an audio or a PDF or something. Then we have similarity check. So in vector databases, there are similarity checks whereby they can use something like Euclidean distance so that when they are trying to search for, okay, let me say you tell them that you're looking for something like cow, it's going to search for all the possible relationships that can, like all the possible things that are similar to that search, and then it should reproduce them. So it can use a mechanism like equilibrium distance where it measures okay, like how close are they to each other. Then we also have storage where vectors are stored in the database, often alongside with what I was trying to say, that when they're storing this, they're going to try to store this in a way that when you are trying to retrieve it, they have somewhere to get the whatever the okay, when you're trying to retrieve it, they have somewhere to get the original data from so that it's very, very easy. Yes. So just like I took you through how the knowledge graphs work, I'm going to try to take you through how the vector databases also actually work. So the first step in vector databases is the same as the first one in the knowledge graphs. There is user input. So the person can provide a prompt of maybe I want a delicious pasta recipe. So when you provide this prompt to the model, it's going to convert the query that you've given it, the prompt, into vectors using an embedding algorithm that is provided. So if it's maybe a video, they'll use a particular algorithm and that. So after converting this to a vector, it's now going to search in the vector databases. It's going to search for all the possible chunks of information that are closely related to what you're searching for. Then after that, it's going to retrieve and bring them back. So you realize that as you're going forward, this is how Google actually works. When you search for something, Google is going to use knowledge graphs, provide what the relationships it knows with that, and it's also going to check its vector, okay, like it's also going to use vector databases to find out the things that are close. That's why you find out sometimes in Google when you're searching it, it also brings up things like people also ask, okay, like people also ask this, or it also brings alternative questions. So it brings chunks of information that are kind of relevant to what you're looking for. So on the next slide, we are now going to actually see how both of them work hand in hand so that we can reproduce good quality information. So let's move on to the next slide and try to understand how both of them relate. So on this slide here, we are trying to combine knowledge graphs and vector databases. So the first thing that we see is user input. When the user sends in their input, it's going to be taken in the two directions. They're going to provide it to the vector side, the vector search processes, and also the graph traversal process, the knowledge graph traversal processes. So when they provide them to both, remember the knowledge is going to pick out relevant information, the keywords that it actually feels it needs. Then the vector side is going to convert them to vector indexes. Then the vector side is going to retrieve things that are similar to what it has indexed, while the knowledge side is going to try to pick out relationships of how these things actually work. So when both of them are done, the other one has picked out the things that are similar, then the knowledge graph has also tried to retrieve the relationships. The information is merged and it's provided to the large language model. So when it's provided to the large language model, it is able to generate and return a final answer that is meaningful. So in this case, we are managing to retrieve information that is up to date without actually training the model 24/7. And then we're also being able we're also being able to retrieve information when it actually has a source. Yes. Thank you very much. I will hand over to the next speaker to take you through the remaining parts of our presentation. Thank you.
Hello, good evening. My name is Eugene Twice, and I'm going to be taking you through the steps in which you can implement knowledge graphs and vector databases for retrieval augmented generation apps and applications. So we are going to explore how to implement these tools, basically a knowledge graph and a vector database, to augment the language generation process when you're dealing with retrieval augmented generation. So we're going to look at from here, from the screen, you can see the first step is loading. So basically here we are loading and pre-processing the text or image data. Then second, we're going to initialize a language model and extracting a knowledge graph. Then we are going to store the knowledge graph in a database so that we can use it for any querying work. Then retrieving the relevant knowledge from the graph based on the user queries. Then generating responses, basically by synthesizing the knowledge that has been got from the language model. So basically, to do this, we require some tools. For example, we're going to be looking at code based in Python, and a library called LangChain library. And also, we're going to use a database called Neo4j, a database. So the first step in this process is loading and preprocessing the text data. So loading and preprocessing the text data, it will help us extract the knowledge graph or the text data from the knowledge graph. So from this code here, we are going to see how it basically looks. So this example here is showing how we get a text snippet describing a company called Prismatic AI and its employers. So from this text, we can see we needed a tool called LangChain. So LangChain is a library that helps with dealing with the large language models and the converting text into processing it into data to store in the database. So we can see this long text. So basically we have a LangChain document underscore loaders import the text loader. So this text loader helps load the text data. Then we have a LangChain.text splitter that imports, where we import the character text splitter. So the character text splitter splits the text into smaller chunks so that it can be processed efficiently. Then we are going to define the text data. In this case, since the data is large, we are going to use the triple quotes, and we are going to initialize it with a variable called text. Then we are going to use a text loader from this input we had above here. The text loader, we are initializing it as loader. So basically what we have done, we're going to load the text data directly from the text variable. Then from the next line, text loader.load returns a list of the document objects. Each is containing a chunk of each of the text. So to split it even to further, we're going to use the text splitter, the character text splitter, which we already imported here. And we are going to give it a chunk size of 200. This chunk size is going to help us ensure that there is a little overlap between the adjacent chunks, which is very helpful when we are dealing with maintaining the context when we are doing the knowledge extraction process. Then we are going to use split documents. So in the previous line, we had a text underscore splitter. So this character text splitter has a method called .split documents that helps to split the documents objects into smaller chunks, which helps us to be stored as a list in the documents objects. So processing this data in this kind of way allows us to prepare it for the next step, which is initializing the language model. So in the next slide, we are going to initialize the language model. So here, we are going to use the OpenAI language model, which is provided also by the LangChain. So we're going to first import OpenAI from langchain.llms, import OpenAI. So basically, we are going to import that and also the transformers. We're going to import the LLM graph transformer. So basically, OpenAI is going to be used as a wrapper for the language model for OpenAI, which we shall use to extract the knowledge graph. Then the LLM graph transformer, it is a sort of a utility class which helps us to convert the text into a knowledge graph representation. Then from there, of course, we are going to need the import get pass and import the OS because we are going to load the environment variable for the OpenAI API key. So we are going to initialize an instance of OpenAI with a temperature of 0, as you can see here. From this line here, initialize LLM, then LLM equals to OpenAI temperature equals to 0. So this temperature parameter controls the randomness of the model's output. So lower values will produce more deterministic responses. So the responses will be able to be determined much easier. Then after initializing that, we are going to create an instance of the LLM graph transformer, as we can see here. When we initialize it, we are going to pass the LLM, which we initialized in the previous line, and we're going to add the LLM object to it. So the transformer converts the text chunks into a knowledge graph representation. Then finally, we are going to call the convert to graph documents method from the transformer import. So you're going to pass the documents into the text lists. So this method uses the language model. We are going to analyze the text chunks and maybe extract relevant entities as the previous discussant said. It contains relationships, entities, and models. So any other structured info that we have, we are going to analyze those text chunks and we're going to extract relevant entities or models and represent them as knowledge graphs. Then we are going to store them in documents. As we can see, we have a graph documents variable. So we're going to store them there, and by doing this whole process, we are going to initialize a language model. Then the next step, we're going to store a knowledge graph in a database. So after extracting the knowledge graph, we have to store it. And in this case, we're going to use the Neo4j graph store. So we're going to import it from LangChain.graphStores, and from that, we're going to provide a convenient interface for interacting with the Neo4j database. Then we are going to create an instance by providing an SI connection details. This is your basic connection. Since we are going to be interacting with the web, we're going to put the URL of that Neo4j website and the username and the password. So it's like your ordinary dealing with databases in your code. So we're going to basically just store this information in the Neo4j database. Then we are going to call the write graph from the graph store that we initialized in the previous line. So from here, we are going to pass the graph underscore documents. That list is going to be got from the previous step and initialize it and then written in the database. Then to explain this further, we have storing the knowledge database, the knowledge graph in this database is going to help us to make sure that this data is very persistent and maybe can be easily queried and retrieved when we need it. So we are allowing for efficient representation and traversal of the relationships. Now, next, we are going to retrieve the knowledge for the retrieval augmented generation. So we have now stored the knowledge graph in this database. We can now create components that will retrieve the knowledge that we need based on any user queries that are prompted by a user. And we are going to generate responses using the retrieved contexts. So first of all, we are going to need llama underscore index. This is a library from llama, and we are going to need three classes. So we're going to need the retriever query engine. We're going to need the knowledge graph RAG retriever, and we're going to need the response synthesizer. So the retriever query engine, basically, it's a query, as it's in the name, a query engine that is going to help us fetch relevant context from a data source. So in our case, the knowledge graph. So we are going to synthesize the response using that very context that you're going to pick. Then using the knowledge graph RAG retriever, we are going to retrieve the relevant information and store it that is stored in the database. Then the synthesizer is going to generate a final response. And how does it do that? It combines the context based on the language model we saw previous steps. Then we are going to create an instance. So to use these tools, we are going to create an instance based on the knowledge graph RAG retriever. And you can see we are passing the storage context, which gives us, which is based on the graph store dot storage context. So basically we are connecting to the Neo4j database that we created in the previous steps. Then we are going to obtain the context from the data chunks that were stored in the database. Then we are initializing the retriever query engine. So basically, we are passing a from args method that helps us handle the entire process of retrieving the relevant context from the knowledge graph, and then we're generating a response based on that context. Then the last step is querying the knowledge graph. So when we're going to, this step is going to help us generate a response. So basically, from the previous step, we are going to define a function called query and synthesize. So what this is going to do, for each query, we are going to use the query engine method to get the relevant context. And then we are going to create an instance of the synthesizer, and we are going to call it a method, the synthesize method, for the query and for the context, for the retrieved context. So we are going to generate a final response to the query, which is then printed to the console. So all these steps will help us to, first of all, load the data into and process the text data. Then we are going to initialize a language model. Then after, we are going to store the knowledge graph that has got from the initialization and store it in a database for querying. Then after, we are going to retrieve the relevant knowledge from the graph based on user queries. And finally, we are going to generate responses by synthesizing the retrieved knowledge based on the language model we created in step 2. So in the next graph, we are going to talk about the various features between knowledge graphs and vector databases. So the first feature we are going to look at is data representation. In knowledge graphs, we have entities and relationships between entities. So this helps us create a graph structure. Then in vector databases, which we use for storing text and images, we are going to use high-dimensional vectors. So each vector is going to represent a piece of information. Then another feature is retrieval mechanism. So in knowledge graphs, we are traversing through the graph structure, following the relationship between each entity. Then in vector databases, it is based on a similarity matrix. So for example, we're going to use maybe a cosine similarity, which returns the most similar vectors and associated information. Then in terms of interpretability, or the way it's interpreted, knowledge graphs have human interpretable representations of knowledge. And then it's a graph structure and it has labeled relationships. Then in vector databases, they are not interpretable to humans due to their high-dimensional representations. So it is going to be difficult to understand these relationships behind this retrieved info. Then knowledge integration, the knowledge graphs facilitate the integration by representing the entities and relationships in a graph structure that is unified. This will help create seamless integration if these entities are mapped properly. However, in vector databases, they're going to be more challenging because these vector databases require you to understand techniques like vector space alignment or ensemble learning methods to combine this information. And then finally, we have inferential reasoning. So in knowledge graphs, it facilitates for this feature by traversing the graph structure and then leveraging the relationship between entities. Then in vector databases, it's a bit more limited because it needs to rely on vector similarity and it may miss the relationships or inferences. However, it can identify similar information, but it cannot identify complex relationships in terms of the vector databases. Then finally, as I explained earlier, this is another sample of the code that creates a knowledge graph using the LangChain and the Neo4j. So basically what happens is it imports the OS model from Python. Then of course, as previously mentioned, we import the Neo4j graph and the OpenAI imports, and also TextLoad and the LLM graph transformers. So we first connect to the Neo4j database, the graph database, using the URL, the username, and the password. Then we initialize the transformer using the LLM graph transformer method. So basically, we have to first set the temperature. As you can see here, temperature is 0, and we get its model name. In this case, the GPT-4 Turbo. Then after, we load the document, which contains this sample data from the database. Then we convert the text into graph objects. So we are converting these texts into graph objects or chunks of data based on the chunk size, as we saw in the previous codes. Then after creating the knowledge graph, we are going to enhance the graph quality in case we want to use it for enterprise use. So using this transformer, we are going to use the allowed nodes or allowed relationships. For example, in this case, we have person, company, and university. Then we are going to set the node properties to true. Then we are going to import again the base model from a import called Pydantic. Then we are going to create a class called sentences that will help use the LangChain model to split the text into self-contained sentences. So here, when we have an input text, we are going to get an output, and it's going to split these texts based on their sentences into different objects. That was all. Thank you for listening.